Thanks, Jonathan. The one and only exoplanets, in fact. Yes. So it's a pleasure to be here today to talk to you about how we, in this FDL 8-week challenge, we've been able to find exoplanets with the TESS, NASA's TESS mission and AI. And I should really start by introducing our team. So we have Megan Ansdell, who's the other astronomy expert. I'm Hugh Osborne on the right. And we have Yanni Ioannou and Michele Sestelli, our machine learning gurus who have helped us out along the way. And a big thanks to all the mentors as well. So I'll start by by jumping too far. So I'll start by covering what Jonathan just covered and talking about what is an exoplanet. So exoplanets are planets like our Earth. They're planets like the planets in our solar system, but they orbit distant other stars. And in fact, when you look up in the night sky, most of the stars you see probably have their own solar systems around them. They might have planets like Earth, they might not. They might have exotic planets that we can't yet conceive. And this is really the reason one of the reasons we study it, to find out what these exotic planets are like, but also to learn something about our own planet and solar system. Is it common in the universe? Maybe is biology common in the universe like ours? But we have one big problem when searching for these exoplanets, and that is space is big. So when we think about exoplanets, they're such faint objects and so far away that it's like trying to search for a firefly next to a spotlight that's in LA from here. So this is a problem that we can't fix directly. We have to look indirectly for these planets, or for most of them anyway. And the most successful method for doing that is to look for the transits of these planets. So if we happen to be looking at a planetary system where the orbit of that planet aligns to bring it in front of its star, we don't get to see this on the left. This is the transit of Venus in 2012. We see the thing on the right. This is called a light curve, and we see the planet blocking the light from that star once every orbit of that planet. And this signal is pretty unique, and we can use it to identify the size of the planet and how far it is from its star. And this has been extremely successful. And one reason that transiting planets is so key is that we can study these planets more than we could those detected by other methods. So for example, these are the 7 TRAPPIST worlds in distance from star and in density. So because these are transiting planets, we get the radius and we can get the mass by other methods, and we can learn something about the compositions of these worlds. So planet E is Earth-like, planets F, G, H probably have a lot of ice around them. And another thing we can do with transiting planets is actually kind of taste or smell the atmospheres. There is starlight when that planet transits its star that passes through the atmosphere and imprints this chemical signal onto the starlight we get during transit. And we can use this, as you'll hear in the future talks from the astrobiology team, we can use this to detect molecules and potentially biomarkers that are signals for life. So this is one of the reasons that TESS is launched, to try and find these new transiting planets. But we do know of a lot already. So this is a graph that kind of shows the transiting planets by distance from the Earth. And we're kind of zooming in at Earth here. This white streak here is all the Kepler planets, where Kepler looked at one patch of sky for a long period of time. But you'll see all these planets are really far away. Most Kepler planets are hundreds of light years away, and we'll never really follow them up in great detail because they're so faint and so far. But you'll see now, when we zoom out again, how TESS is going to change that picture. Suddenly, these blue points are the predicted planets that TESS might find. And you'll start to see this swarm of nearby bright star planets where we can suddenly do a lot of these interesting techniques to find the composition and potentially find the atmosphere and look for things like biomarkers. So this is really going to be key, and this is why TESS was launched earlier this year. So what is TESS going to do, and how is it going to find those planets? TESS, it has these 4 wide-field cameras, each staring at a different part of the sky in sort of a line, and it observes the same sector of sky for about a month. And then every month it switches to a new position. And that means in total, over a course of a year, we get almost the entire sky with at least a month of data. And in the pole here, we get a full year's worth of data, which allows us to find longer period planets. So this is the kind of data we're going to get down, though. These are 4 CCDs from TESS. In fact, these are simulated data because it has only just launched, so we don't have real data. We have 4 sectors worth, like this, of simulated data from the pipeline that the NASA Ames people have provided. So these are the images, but we focus on 16,000 target stars in here. There are hundreds of thousands of stars that might have planets in. And we get about 21,000 images for each of those target stars. Now, we could try and search for planets here, but what we tend to do is turn these into light curves. So this is less than 1% of the light curves we get each sector. And somewhere in here is that dip signal I showed you at the start of transiting planets. But it's kind of difficult to see. What you do see is a lot of these drops. These aren't planets. What these are is just systematics in the data. So there is a lot of things that happen on the spacecraft, thermal events, these oscillations, cosmic rays, and these can look like planets. So there's a lot of systematics there. So what we tend to do is we process out these systematics and then we search for periodic signals because we know that planets come around once every orbit and we should see multiple of these transits. So that once we do that and search for these transit-like signals, we get a big bunch of candidates that look, they look like dips in a periodic fashion. So these are our planets, right? Unfortunately, there is a lot of other things out there in the universe that mimics planets. We have stars that pass in front of each other, which are called eclipsing binaries. Sometimes these happen in the background of the star we think we're looking at. And as you've heard from the Space Weather Team, there's a lot of stellar activity that happens on the stars that can sometimes mimic transits. So this is really the crux of our problem when it comes to transiting exoplanet detection. How do we go from all of these candidate planets to knowing where the planets are? And maybe if we can do this really well, we could even go back to those light curves I showed and figure out which ones the planets orbit. And if we're feeling extremely adventurous, we could go all the way back to those pixels and directly classify which ones have planets around them. Ooh. So what do we currently do to find these planets? We don't go to the pixels, in fact, we go from the detections usually. And yes, we still manually look at these light curves. We do use statistical and automated techniques to kind of chop down to the most likely candidates, but there is still a lot of manual vetting. And in fact, for a smaller test set than we had, took 18 humans, about 300 human hours in total for one sector, and they got a 94% accuracy. So this gives us a baseline of what we can kind of aim for to improve. And as you might be aware, the test planets are really important because we can follow them up, and we really want to follow them up rapidly because these planets are going to disappear out of view behind the sun for a while, and we want to observe them before that happens. So we have this time pressure that means that maybe having 18 humans staring at light curves might be too slow. So what are we going to do to solve this problem? Well, I mean, you know what we're going to do. We're going to use AI or machine learning. So we're not starting from nothing here. There was a paper last year that we adapted by Chris Chalou, who looks at the Kepler data to try and find out which ones were planets and which ones weren't. So we adapted this, but we made the network a hell of a lot smaller. So we went from all of these layers to just 5 layers in total. We also added some extra information like stellar parameters and the motion of the star, which tells us something about what's causing the transit. And we added balancing, because this is very unbalanced data. There's not many transiting planets in the data. And in total, we do much better. So top right here on this PR curve, precision recall, is where you want to be at. The black curve is what happens when we recreate Chris Chalou's method. And then each thing we add, star information and the centroids and the augmentation, brings us close to that corner. And we do about 2% better and get up to 96% precision on Kepler, which means we can recover more planets. We can get about 90 more planets on a single model than Chris could. And it also, because it's so small, it's very rapid to run. We can run this model in a minute on new data. And we can do it on test data as well. So we tested this on TESS, and we got similar numbers, about 96%, so better than humans, and obviously far faster. We can do in 30 seconds what it took humans 300 human hours to do. And we also looked at, rather than just planet, not planet, whether we could classify some other signals. So these are similar curves, but they account for binaries and a background eclipsing binaries. And we do almost as well, about 94%, but we do get some confusion between the different classes. But this could be useful for follow-up because we want to know what we're looking at and what could be an eclipsing binary or what could just be noise. And when you could go back a step further. Once we've trained this model, we can go back before we eliminate some of the candidates and maybe run it on the pre-statistical objects. And actually, when we do that, we recover almost the same as these statistical tests that were initially used. But we also recover some planetary signals that were missed by those classical tests. So some of like this object down here is a small radius planet that was previously missed by the detector and that wouldn't have been detected by AI. And we can also go to the light curve. We had a go at trying to turn these light curves by period folding into images. This is an image in period phase space. And images are perfect for machine learning because we can use something like ResNet. You know, it normally works on cats and dogs, but we're running it to try and find these planet signals, which, because these get folded at only a particular period, the right period stacks up, so we see these bright points where the planet signal is. And we do pretty well. We get 91% accuracy on the Kepler candidates. But again, 8 weeks isn't enough for some of these things, and we need a bit more time to do this. And similarly, we went all the way back to the pixels, all of these month-long videos. But unfortunately, there's a lot of noise, and we're still working on trying to improve this. But if we can get this working, it would bypass the TESS pipeline that takes a couple of weeks to run and immediately tell us which stars have planets around them. So with that, I'll just summarize that we can classify these test planets faster and more precisely than previous approaches in 3 orders of magnitude more faster, and also 2% more precise. And we've also developed these innovative new techniques for hunting planets directly from the light curves and also directly from the pixels. And I don't think it's a stretch to say that maybe in a couple of years when TESS or another transiting planet mission finds a rocky planet that has biomarkers in its atmosphere, it may well have been detected by machine learning techniques like this. Thanks very much.